All right, thank you very much. Hello, everyone. I'm very happy to start this session today with our speaker, Enrique Torres-Giese from Trinity Western University. And Enrique will be talking about sequential motion planning assisted by group actions. Please, Enrique.
Thank you, Jesus. Thank you for the invitation. Okay, so let's get started here. Okay, so I'm gonna have to hide the Zoom with the faces and, well, the information about who's here. So if you have any questions, let me know. Okay, so as you can see in the screen, well, the title of the talk is Sequential Motion Planning Assisted by Group Actions. So the emphasis of the talk will be in the second part in what we can say about group actions assisting the motion planning when we study this problem of planning in a space. So here I will be assuming that we have a space X with a G action. So here we have a group G acting on X. And then let me get started by posing this question. How do we take advantage, how we incorporate the group action into the study of the motion planning problem? So of course, there's many things that we can say. There's a number of perspectives that we can study, investigate. I will be focusing especially on one, although I will be making a few comments about other ideas, other perspectives that could be given as part of an answer to this question. So how do we make use, how do we incorporate the group action into the study of the motion planning problem? Now, to avoid pathologies, special cases, corner situations, I will be assuming that the spaces that I will be discussing in the talk will be nice spaces. That means essentially Hausdorff spaces, path connected, locally path connected, compact, and I guess also at some point I may be using locally contractible spaces as well for some specific bounds. Okay, so again, the emphasis is in this keyword. How do we incorporate the group action? So one perspective, as you can see on the left-hand side, is to say, well, how about if we make or we request the motion planners to be compatible with the group action? Well, that's, of course, something that has been done. For instance, in the work of Coleman and Grant, they define equivariant TC, again, by requesting the motion planners to be compatible with the symmetries of the space. Another approach by Dranishnikov, he defined in a similar way what he calls strongly equivariant TC. And in the work of Lubatsky and Marcentowicz, they define invariant TC. So all of these concepts on the left-hand side, again, make use of this idea of saying, okay, if we want to incorporate the group action into the study of the motion planning problem, maybe we can request to start off the motion planners to be compatible with the group action. So that's one way, but I will be focusing on the perspective that is on the right-hand side. So what I want is to take advantage of the group elements to make them be part of the motion planners. So that's the perspective I will be discussing with you. And here the keyword is I want them to be part of the motion planner. So there's at least two definitions already available that take this perspective into account. One of them is the definition of the effective TC due to Blasik and Kaluba. I will be making some comments about this in a few seconds. And there's a slightly newer perspective or newer notion of TC in this context, and it's the so-called effectual TC, defined by Kadavith, Gutierrez, Gonzalez, and Ipanaki. So I will be working on the right-hand side, and I will be explaining what we can do to define higher notions of these concepts of effective and effectual TC. Okay. So I'm going to start off with some basic definitions. So here's the definition of Blasik and Kaluba of effective TC. So what they do is that they consider this space PG2 of X. So essentially what they have is pairs of paths, alpha 1, alpha 2. And what they say is that, okay, so we want them to satisfy this condition that is on the right-hand side. That is that the end point of the first path should be in the orbit of the start point of the second. So we can speak of this as being like broken paths. And it's fine because, again, we're assuming that we have a group action. And we can think of the group action as some kind of like external system assisting the motion planning. So in this perspective, again, we say, okay, this is fine, no worries, because the group action, again, is some kind of like autonomous system that is going to help us to complete the motion planning. So what they do is that they take this space and they take the, let's say, usual evaluation map. So they take the pair alpha 1, alpha 2 to the endpoints. In this case, the start point of the first one on the left, and then the end point of the second one. So this function, this map, happens to be a vibration, and well, they defined, this is Blaszczyk's and Kaluba definition, they defined the effective TC as the sectional category of this map. Okay, so that's this definition. So there's a refinement of that one. This one is due to Cadavid, Gonzalez, Gutierrez, Ipanaque. The construction of the total space of the vibration that they use is similar, but in this case, what they do is that they say, okay, we're going to keep track of the element in the group that we need for the gluing of the broken path. Okay, so that's the condition now here on the right-hand side that we say, okay, we have a specific element helping us to complete the motion from the start point on the left to this target point on the right. So this evaluation function, in this case, is essentially just taking, again, the endpoints, forgetting the group element. And well, this one happens to be a vibration, and the definition of the effective TC in this case is, again, the sectional category of this function. So let me emphasize again, in this perspective, we are assuming that the group action is important here, some kind of like autonomous external system helping, assisting the motion planning. So we're happy, we're fine with a broken path like this because the system, the external system, the group action will be taking care of the motion planning. Okay, so some properties. So these two versions of effective TC happen to be G homotopy invariants. And as you can see in the second property, they are essentially approximating the regular TC of the space. So we have this condition. By the way, the construction of Blaszczyk and Kaluba can be extended to more pieces, to more components of the broken paths. I'm not going to get into those details. The construction I showed here is with essentially two components, with two pieces. Likewise, the construction of Gonzalez and Cadavid, Gutierrez, and Ipanaque can be extended with more components in the paths, with more pieces, but they show that it's not necessary, that it suffices to consider only two. Okay, so I will be paying more attention to the one in the middle, the definition of effective TC. Let me just scroll up here, the one that keeps track of the group element. The main reason why is because, as you will see in a moment, this one is the key, well, let's say part of the process that will allow us to make a connection between this perspective and the TC of the quotient space. So that's why I want to pay more attention to this one. Okay, so we have these properties. And well, there is a third way we can again try to study the motion planning by incorporating the group action, and is by defining this notion of TC called effectual TC. And well, the definition is the following. So we're going to take the usual evaluation function, as you can see on the right-hand side. And then once we land in the Cartesian product, we're going to send the points to the first factor being just the identity, and then the second one using the quotient map. So if you take a map, essentially you are sending, well, a path, alpha, you're sending that to the start point, and then the second one would be essentially the orbit of the nth point of alpha. Okay, now here, and from the rest of the talk, I will be assuming that we have a finite group G acting on a space X. So that is implying, for instance, that this composition that we have on the right-hand side is going to be a fibration, so we can speak of the sectional category. Okay, so now let's try to understand a little bit what is this effectual TC doing. Well, if you think of motion planners, if you take an effectual motion planner, essentially a section of this composition, so like this, well, the source data or the initial data is this point A and then an orbit. So what the planner is constructing is a path connecting the point A with a point in the G orbit of B. So we are happy again with landing in a point, say, that is part of the orbit of B, because again, we're thinking of the action of the group on the space as an external system that will be assisting the motion planning, will be completing the motion. So that's fine. So we have essentially this construction here for the effectual TC. Okay, so some properties. This one happens to be also a G homotopy invariant. And well, it can be proved, it takes a little bit of work, but it can be shown that the effective, the effectual, and the TC of the quotient space are related in this way. So now we have the effectual somehow like bridging or connecting the effective and the TC of the quotient in this way. And again, we can think of them as some kind of like approximation from below to the quotient, to the TC of the quotient. Okay. So now what I would like to do is to say, well, what is what we can do in higher cases in sequential motion planning? So I'm going to use this space m sub n of x or mgn of x. So here, so that you have an idea of what I'm referring to, mn is for me a multi-path or the space of multipaths. So some people use this notation, so they take the paths or functions from the join of n copies of the unit interval into x. So that's why I'm using this notation. So you have a join with n copies of the unit interval, and well, you're taking paths or multipaths into x. Okay, so like in the case of the effective TC with only two pieces, in this case, we're going to keep again track of the group elements, as you can see here. And what we are saying, well, we have this definition, is that we are taking broken multipaths, and the condition that we have now on the right-hand side of the description of the space MNG of X is that the start points have to be in the same orbit. So they are emanating, broken multipaths emanating from the same orbit, and we are keeping track of the gluing elements. Okay, so turns out that this is a fibration. If you take a tuple like this and you look at the endpoints of the components alpha 1, alpha 2, and so on, well, this one is a fibration. So this is now telling us that we can define the higher TC, effective TC, as the sectional category of this function here. Now, it can be proved, takes a little bit of work, that if you have a principal action, or for instance, if you have, like I was assuming just a few seconds ago, a finite group acting freely on a space, you can waive these elements in the definition. So you can forget them. And well, the condition would be essentially here requesting that these points would have to be in the same orbit. And they will yield the same value for the sectional category. So you have an analogous evaluation function like the one I have here in the definition, just taking the endpoints. And well, again, you can waive those. So it's fine whether you keep track of the group elements or you forget the group elements if you have a nice action, let's say a principal action or a finite group acting freely on a space. Okay, for the effectual TC, what I will be doing is the following. I will be taking essentially the usual evaluation function into the Cartesian product. and then taking the following map, so the identity on the first factor, and then the projection in the remaining factors. Okay, so in terms of motion planning, what this is doing is, well, if you have this initial data, what we are doing is constructing a multipath in X. So if you want a section going in the opposite direction, S, well, this is constructing a multipath in X. The first component in this notation alpha 0 is reaching the point that we have here, A, but the other ones are reaching points in the orbits of the corresponding targets. And again, this is fine in this perspective because we're thinking of the group action as an external system helping us to complete the motion planning. Okay, so now we have these two notions of higher effective and higher effectual TC, and we can also define a higher notion of orbital TC. So here in this case, what we have is just the evaluation function, the usual evaluation function, and then the quotient into each of the factors. Okay. So if you notice, this one is very, very similar to the previous one, the higher effectual. The only difference is that now we're taking all of the factors of the Cartesian product on the right-hand side to be the quotient space. So it's very much the same construction. And again, in terms of motion planning, well, in this case, what we are saying is that we will be happy if we are reaching points in the orbits of the target points or the target orbits. Okay, so now we have these three notions of effective, effectual, and orbital TC. Okay, so some properties. These three happen to be G homotopy invariants. Okay, and well, it's possible to show that they are related in this way. You have these inequalities. And well, now this time we have the orbital approximating from above the TC of the quotient. Okay, so there's some work that has to be done to show the inequalities. Is fine. It's possible to show that we have these relationships or these inequalities. And well, I was along the way saying that we have these vibrations. So based on that, we can say, well, if you have vibrations, you can also use the traditional homological lower bounds, in this case, for each of the functions, maps affording these concepts. And therefore, we can speak of effective, effectual, and orbital zero divisors in the usual way. Okay, so we have some tools. We have homological lower bounds. We can also use some dimensional, and in some cases, some connectivity related upper bounds for each of these invariants. Okay, so here's another property that I will be using is something that perhaps some of you have seen before. I guess is kind of like a traditional, or let's say classic proof for this kind of fact here. So the effectual TC, the higher effectual TC is bounded below by the category of the Cartesian product, n-1 Cartesian product of the quotient. And the idea is simple in this case. So I'm going to mention what you can do to proceed in this case. So what you do is that you fix a point in X, let's say X naught, as you can see here. And then you take the inclusion afforded by the inclusion map afforded by X naught. And then, well, the idea is that I want to use an effectual motion planner to define in this case, categorical set in the Cartesian product of X modulo G. So what we're going to do is we're going to say, well, take the projection P1 onto the first factor. So that's the function I have here on the left-hand side. And then take the inverse image of the point X naught and intersect this with the domain of the motion planner S. So that's going to define a set W here. And well, of course, the inverse image of the point that we are fixing here is going to be homeomorphic to X modulo G, Cartesian product, n-1 times. So the graph or the illustration that you should have in mind is something like this on the right hand side. Okay, so remember the effectual one is going from, in this case, the the space of multipaths into x times x modulo g. So this is the, oops, my apologies here. This is a function affording this concept, and I was too close to the edge, so that's supposed to be n minus 1. Okay, so what we are saying here is, well, in this illustration I have over here on the right hand side, we have a multipath, and this one is reaching the first point, x naught, and then is reaching other points in the orbits of the corresponding targets. So what we're going to do is to say, well, use this information. So here's a, let's say, recipe. In practical terms, essentially what we're saying is reverse these functions, these paths. This is happening in x. Okay, go to this point, and then use the first path. In this notation I have over here, it would be alpha naught. And well, essentially, again, this is happening at the level of x. Then the next step is to say, well, go to the quotient and essentially glue each of the functions in this notation would be, or paths, alpha 1 all the way to alpha n minus 1 with alpha naught using this orientation I was just telling you. Go in reverse in the opposite direction and then use alpha naught. So that's what is happening here. And well, this is essentially telling you that you have a contraction for W, and therefore you have this inequality, that the effectual TC is bounded below by the category of this Cartesian product of the quotient. Okay.
Enrique, is it possible that that inequality holds also for the effective TC, the higher effective?
I'm not so sure. I perhaps can come back to your question at the end. Let's see. So for the, let me just try to think just for a few seconds for the effective. So for instance, if we have a nice action, a nice space and a nice action, for the effective, what we are constructing is essentially this, considering this function. So yes, you could proceed in the same way, but you're not going to have the quotient over here on the left hand side. Okay, that's what I can say here on the fly, on the spot. I don't think you're going to have the quotient x modulo g. Okay, but I can come back to that, or perhaps maybe we can talk about this later. Okay, so another property here that is kind of technical, and well, it's just telling us that the openness condition of the domains, usually we define sectional category. By the way, let me pause here for a second. The definitions that I'm using are unreduced. And well, here back to this comment, the openness condition, the traditional openness condition of the domains can be replaced by the following. If you have a nice space, you could just simply say, take the domains to be E and R's and just take them to be mutually exclusive. And that will be essentially defining the same number in each of these definitions. Okay, so I see that I'm kind of like going faster than faster than what I was expecting. So I will be mentioning just a few more calculations and then tell you a little bit more about some other calculations that I have already completed. So here, the example I want to explore with you is the case of the antipodal action. So this is the action of the group of order 2 on the m-dimensional sphere. So let's see, for instance, what we can say for the effective TC. So I'm going to construct a motion planner in the following way. So to start off, we're going to define u sub j here. Change the order to perhaps this. This is going to be the subspace of this Cartesian product consisting of tuples with the condition that exactly j components will be different from the first component in this notation x1. Okay, so that is essentially defining a partition. You can show that these are E and R's. So this is one of the ingredients that we will use. And then one more ingredient here is that I'm going to define this function alpha as follows. So what is alpha? So if you have a couple of points on the sphere, so x and y are on the sphere here, x and y are on the sphere, and they happen to be different, then I'm going to take alpha to be essentially the shortest path from negative x to y. And notice in this case I'm safe when I say the shortest path because negative y is not negative x. So the antipodal of y is not negative x. So we can speak of the shortest path. And if the points x and y happen to be the same, we're going to take just the constant at x, well, the constant at these points, x or y. Okay, so with this definition, the motion planner I'm going to define, notice I'm talking about the effective TC, and in this case we have a nice action, is in this case a free action of a finite group. So I can waive in the definition of an effective motion planner the group elements, and that's what I'm going to do here. So I'm just going to say, well, the motion planner in this case is going to be defined in this way. Essentially just use alpha to connect x1 with x1, x1 with x2, as you can see here, and proceed in the same way with each of the points. And well, alpha is essentially telling you what's the way you should be proceeding or you should be following to connect these points. And remember, in this case, we're happy with connecting either, in this case, the point x1 with x2, or at least negative x1 with x2. And that will do, because that's essentially the purpose of this perspective in effective, effectual, and orbital TC, that we're thinking of the action as helping us, assisting the motion planning. So that is telling us that we have this upper bound. The effective TC is less than or equal to n. Okay, and well, for the lower bound, well, there's some work that one has to complete. But the idea that it suffices to recall, to check that this evaluation function that is affording the effective TC is essentially the vibrational substitute of the saturated diagonal. So what is the saturated diagonal? Well, it's essentially this function here. So we are translating the point x using this data, these group elements. Okay, so it's possible to check that we have a lower bound that happens to be also n in this case, and therefore we have this calculation that the TC effective of the sphere is equal to n. Okay, for the effectual TC, you just noticed a few seconds ago that I was saying that the effectual TC is bounded below by the category of Cartesian product x modulo g n minus 1 factors. So that's what you see on the left hand side, okay, right here. And then on the right hand side is just the usual category bound using the base of the map affording the effectual TC. So once you have these inequalities, you can show very quickly, you can check very quickly that we have these values on the left hand side, m times n minus 1 plus 1, on the right hand side, one more. So this is just one unit away from being optimal. And well, it turns out that it's possible to settle the calculation, at least, well, actually, in any case of the value of n, but at least in the case n equals 2, you can find this in the work of Cadavid, Gonzalez, Gutierrez, and Ipanaki. So they constructed an explicit effectual motion planner in the case when m is 1, 3, and 7. So they are suggesting that potentially this calculation could be recasting the Hopf invariant 1 problem, potentially. Okay, well, it's possible to show that this situation can also be settled in higher cases. So it's also possible. Now, for the orbital TC, what we have is this. Essentially, here we have this function, this composite. You can take either one, the upper one or the lower bound, sorry, or the lower composite to define the orbital TC. And well, in this case, using just basic zero divisors here. So for instance, if you take the degree 1 generator of the modulo 2 cohomology of the projective space, that's going to go to 0 here on the left hand side, assuming m is, I guess, greater than 1. And well, just using this information, you can get this lower bound on the left hand side. Okay, so that's enough to show that the orbital TC of the sphere is given by this expression, n times m plus 1. Okay, so here's an example. So for instance, here, in the case when we take the 4-dimensional sphere, the effective TC, we know that is equal to n. So in this case, okay, let me mention here, this is n. Okay, so we get a 2 for the effective TC. For the effectual TC, in this case, well, according to what I was just explaining right above, we know it should have to be n minus 1 times m plus 1 plus some number delta that could be either 1 or 0. So in this case, we get this calculation. Let me just scroll up to double check I got it right. Is m times n minus 1? Yes. Oops, right here. Okay. In this case, for instance, for the TC of the quotient, this is the projective space. You can obtain this using, for instance, the classic result that the TC of the projective is the immersion dimension, essentially, plus 1. Or you can, well, notice that this is a space with fundamental group, the integers modulo 2. Therefore, the TC, the 2, order 2, or degree 2, regular TC is essentially 2 times the dimension. The orbital TC would be, in this case, n times m plus 1, so that's why we get this value. Okay, so as we can see in this example, these numbers may be all of them different, like in this calculation, so we're computing different invariants. And well, in general, what we have from one of the properties that I mentioned just a few minutes ago, we have this connection. Now, what is interesting here is that the value of the TC of the quotient is oscillating between, of course, this one over here and these, and it can be as low as the one on the left-hand side. For instance, when m is 1, 3, and 7. Okay, so it could be the lower bound, or it could also be the upper one, for instance, when m is a power of 2. Okay. So just a few more comments before I finish my talk. Is also
Enrique?
Yes, let me.
I might add that, by the way, this answers my question that the lower bound in terms of category is not does not work for the effective in the effective case. In this case,
Yes, yes, because well, as you can see here in this example, is very low. Okay, so just a few more comments. So I have already completed some calculations. I know this is just like, wow, too many things in just one spot in table. So here, for instance, in this case, let me use a different color. I have the effective in the first column, then the effectual, and then the orbital in the corresponding columns. So for instance, what I was sketching just a few seconds ago was essentially this row here, these calculations. And well, I have also completed all other calculations for other actions, like for instance, the reflection action. This one, of course, is not free, so I only completed the calculations for the effective. The rotation action. Okay, so this one is rotation by 180 degrees. And then in this case, we have these calculations. Okay, so some of these are extending calculations done by Cadavid, Gonzalez, Gutierrez, and Ipanake. And well, actually, the ones by Ipanake, Gonzalez, and Gutierrez, and Cadavid are essentially these in the antipodal case. So in the rotation action, these are essentially new calculations. So the calculations mostly depend on zero divisors in the corresponding cases, and some upper bounds in terms of dimension. So that's essentially the way you can get these calculations. Of course, there are some values, as you can see here, that are not complete. We don't know what is the value. But as I mentioned, for instance, at least in the case of the sphere, there are some cases that are settled. So I'm going to stop here, and well, let me know if you have any questions.
Thank you very much, Enrique. All right, let's give some time for people to ask questions or make comments.
Well, maybe I could ask something. So you said that these invariants are all related to TC of the orbit space.
Right, in this case.
Yeah, so are there any special cases where you hope to be able to calculate higher TC of an orbit space by hoping that these things coincide, the upper and lower bounds coincide?
Yeah, so that's kind of the philosophy behind this. I don't have an explicit example where, for instance, the 3 on the right-hand side would agree, would give you the same value. And that's work in progress. So at this moment, I'm paying more attention to the orbital TC to see what is what we can say, for instance, to bring it closer, or in what cases we can bring it closer to the TC of the quotient. But yes, that's kind of the philosophy behind this perspective.
Mm-hmm. Is there any relationship between the orbital TC and orbital configuration spaces?
Good question. Yeah, so that's again work in progress. Yeah, so there's other calculations that could be, of course, of interest, like for instance, configuration spaces, orbit configuration spaces. You have natural actions. Yeah, so that's something that would be, of course, of interest. And again, work in progress.
Okay, thanks.
Okay, I think this is a good place to stop the recording. I'm going to stop the recording.